Okay, this is the lab midterm. So position time data, use the data to create a graph of velocity versus time for the same object. So here is my time and my position. So how do I calculate velocity? So there's more than one way to do this, but the way that we did this in the lab was to say Bx equals delta x over delta t. So if I want to calculate V2 at the 2 position, that's going to be x3 minus x1 over t3 minus t1. So this first v, I'm going to skip that one. This one is going to be equal to, I'll write it out, it's going to be equal to 1 minus 0 divided by 0.4 minus 0. And that goes right here. And then the next one I'm going to calculate V3. It's going to be x4 minus x2 over t4 minus t2. So every time if I want to calculate the velocity for this, I'm going to use these two changes in x and these two changes in t to get a more average. And so I did that. I did it in a spreadsheet. So these are my values for velocity based. So this 2.5 is 1 minus 0 divided by 0.4 minus 0. The next one, 5, is going to be 2.1 minus 0.1 divided by 0.6 minus 0.2, and so forth. And there you get that. And then I plotted it right here. And I didn't label it, I'm sorry. So this is time, and this is velocity. And if you want, you could add a straight line. I didn't ask you to do this. I probably should have. That, and it's actually fairly linear. If you found the slope, which I didn't ask you to do, that would be the change in velocity over the change in time, which would be the acceleration. Awesome. Okay, that's that. That's that one. That's that one. Number 2. Here are two balls moving, and the question's when and where they meet. So let's look at, they both have constant velocity. So I need to find the slope. Let's see. It doesn't have to be perfect. I'm not gonna count off for imperfections. It's just a test. Okay, so we'll call this 1, and we'll call that 2. Oh, let's call it A and B. Okay, so VA is going to be slope of A. So that's going to be, I'm going to pick some values right here. I'm going to pick that data point. Normally I shouldn't pick the data points right there, but I don't really care. And that one. So it's going to be the change in position. So it's going to be final, which this is going to be about, that's 100. That's about halfway. So I get 125 centimeters minus 150 centimeters. All of that over 0.8 seconds minus 0.2 seconds. And so this is going to be negative 25 centimeters over 0.6 seconds. I got my calculator right here. Bring that down. Drop. So I get 25 enter 0.6 divided by, I get negative 41.6, let's just say 0.7 centimeters per second. Now what I really want is the position of A as a function of time. So XA as a function of time is going to be equal to the initial position, which is right up here. Let's call that 150. So that's about, let's say 160. 160 centimeters plus, that's the centimeters, plus the velocity, which is negative 41.7 times t. So that's my equation for x. Now let's do this for b. Again, I need to find the slope. So let's pick this point and that one, which I know is terrible. So VB is going to be equal to, it's a little bit less. I'm going to say 20 minus 0 over 0.6 minus 0. So 20 over 0.6 equals, calculator, 20 enter 0.6 divided by, and I get 33.3 centimeters per second. Now for its equation, xb as a function of time is going to be, it started at 0, so it's going to be equal to 0 plus 33.3 t. So now I want to know when these two meet. Sorry, you can't see that. So when do these two meet? Well, they meet when xa equals xb. So let's set these two equal to each other, and then I can solve for t. I'm going to drop my units just to make things look nicer. So I get 160 minus 41.7t equals 33.3t. So now I'm going to add that to both sides. I get 160 equals, let's see, this has to be 74.75, right? Did I do that wrong? 75t. Okay, let me just check real quick. 41.7 plus. Yeah, 75t. Now I can divide both sides by 75. And I get t equals 160 divided by 75. And I get 2.13 seconds. That is when. Where I can put that value into that time into either one of these two equations. Let's use the bottom one because it's a little bit easier. So xb at 2.13 seconds is going to be 0 plus 33.3 times 2.13 equals, let's see, so I get 2.13 enter 33.3 times. I get 70.9 centimeters. That's where. So if you looked at, if you were to take these two lines and keep drawing them until they got to the same thing, they would meet right there in the middle probably. Cool, 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 cool. No doubt. Okay, here is a frictionless car. Let me move my calculator. I'm kind of getting offset here. Ramp is raised, greater sine angles, and here's a plot of f versus sine of angle of the ramp. Use the graph to find the mass of the car. Okay, so let's look at this slope in general. So if I have a slope like this, and there's my thing, I have this, I have the weight of the car, mg, I have the tension, the normal force, and then I have the force pulling up, F scale. And these are all vectors, I guess. So I know this value. And if I call this the x direction, then F net x equals 0. And so that's going to be Fs minus, this is the angle theta, we did that, minus mg sine theta equals 0. So if I put Fs equals mg sine theta, then and I plot this variable versus this variable, this is like y equals mx plus b. So that has to be the slope. So if I find the slope of this, it's equal to mg. So let's do that. Okay, so I'm just going to pick a value about right. I'm going to use the 0 point, which isn't always the best idea, but I'm going to do it anyway. And I'm picking a point. Let's just go right there. Okay, so the slope is going to be this y value, which is going to be, let's say, 14 minus 0 divided by 0.8 minus 0. So I get 14.8 divided by, I get 17.5. Now, 17.5 is equal to mg. And I asked for the weight, the mass. So if I divide, so g is 9.8. So m is going to be 17.5 divided by 9.8 equals 9.8 divided by. And I get 1.79 kilograms, the mass. Okay. Ping pong ball before and after hits the can, estimate the speed of the can before and after. So we've done this before. Find the slope, because it's position versus time. So this is the slope beforehand. I'm going to use this. And then afterwards, it's not the same. I'm going to use this. Okay, now here, you have to be very careful. This one, because it does not necessarily go through the origin, so I definitely want to use the slope. So before v1 is going to be delta x over delta t, so I need to pick some points here. So let's pick this point and this point. And if you're approximately okay, I'm fine with that. So this is 40, 50 would be halfway, so let's say 55 centimeters minus this position, which is going to be, let's see, 30, let's say 37 over the time of 0.019 minus 0.018, and I get drop 55, enter 37 minus 0.019, enter 0.018 minus divided by. I get 18,000 centimeters per second. Now after, same thing. So I just need to pick some value. Now I can use it anywhere on this whole line, right? I'm going to use this one, and I'm going to use, I like to pick the ones on the times. Let's put that one. So V2 is going to be delta x over delta t. Yes, that's sorry. So that's going to be equal to this value of, let's say, 81 minus 50 over 0.021 minus 0.018. So I get 81, enter 50 minus, I could have done that in my head, dummy, 0.021, enter 0.018 minus divided by, and I get 10333 centimeters per second. Done.